Okay, I think we can start. Thank you, Claudio. It is a great pleasure today to have Laura Veldkamp as a speaker. Laura is a professor of finance at Columbia University. Her research is about understanding how people get their information and how that information affects the decision of firms and individuals, and how their decision in turn have macroeconomic effects. And today, Laura will present this paper joined with Jan Eickhout, titled Data and Market Power. So Laura, you have 45 minutes, and please, everybody, don't forget that we take questions for Laura at the end of her presentation. We reserve 15 minutes just for questions after the presentation. Please raise your hand so that at the end of the 45 minutes, we will give you the floor for your question. And please, Laura, the screen is yours.
Thank you very much. Thanks for being here today to learn about this data and market power. This is joint work with Jan Eickhout, who's at Pompeo Fabra. There we go. Nope. Okay. So our question is, has big data made big high markup firms? And so there's a lot of discussion in the press right now about data, the new data economy. Is data causing lots of problems? There's good reasons to worry about this. Data has economies of scale, as we'll talk about. Big firms should benefit more, and in the empirical evidence suggests that big firms are benefiting more. So a bunch of work done by Erik Brynjolfsson and a whole host of co-authors documents this. And I want you to have in mind not just the big five. Obviously, the Amazons, Facebooks, and Googles of the world benefit enormously from data, but there are a lot of regular product firms that are bigger than average, that are making more use of data too. And so I want you to have some of them in mind. And we're going to ask, should data produce more market power? What should that look like? What should we be looking for in the data if we want to investigate this question? So, whenever we talk about market power, one of the key measures of market power that immediately comes to mind is markups. So one would then want to ask, have markups risen? And here the literature is split. So market-wide markups suggest rising market power. They are going up, and a lot of people have interpreted this as saying markets are, on average, less competitive than they were a few decades ago, and also suggests that those markups are counter-cyclical, that being an important ingredient in a lot of new Keynesian models. But if you look at markups measured differently, maybe at a more disaggregated level or product level or even a firm level, those markups look a lot more stable. They don't seem to have these long-term trends, and they don't look counter-cyclical. So we've got this evidence that people are arguing about, I'm right, you're wrong, measured in slightly different ways. And so we're going to try to make sense of the evidence that's already out there. So our question is, if data-intensive firms grow bigger, how should that affect markups? And can this help us make sense of the conflicting evidence? So two key themes in this talk. The first is that there are competing effects of data on markups. It's not always going to be that data increases markups or that data decreases markups. The answer there is going to be, well, it depends. Markups aren't really the right place to look if you want to know what effect big data is having on markets and even market competition. So data is going to lower risk. So risk is going to be an important part of the story here. It's not normally a part of the story we talk a lot about when we think about firm competition and markups. But I'm going to argue that if we want to start thinking about data's role in markets, we have to consider risk. So data is going to lower risk, and that's going to push markups down, but it's going to raise market share, and that's going to push markups up. So we'll have these two competing forces fighting against each other. But what we will see, this isn't a paper that says when data grows, anything goes. We're going to see that data produces markups that systematically increase at higher levels of aggregation. So that will explain the split in markups being measured in different ways. Okay. So main ideas and outline. This is a theory paper. I'm going to talk to you about a model, but a model that's really designed to speak to the set of facts that are out there and try to make sense of them. So important ingredients in the model are that data is information, right? It's a digitized information. At some level, we know that, but there are lots of people modeling data, thinking about data as being like an advance in TFP, or thinking about data as being kind of like a, physical asset that you just can't touch. But we're going to take seriously the idea that data is really information. And what is information at its essence? At its essence, information is a tool to resolve uncertainty or risk, right? So if that's the essence of data, then starting from a model that has no role for risk, that has either no uncertainty or no aversion to uncertainty, no price of risk, seems like a non-starter. So we're going to model this as uncertain consumer demand. There's a firm that will say, I don't know how much my customers will like blue shirts today. I'm trying to figure that out. I'm going to use some data to try to forecast that. Or maybe how much they like, black shoes or anything else, right? And so they'll have a bunch of products, and they're trying to figure out which of these should I produce, which are going to have higher demand and get higher prices and so forth. This is really just a stand-in for any kind of uncertainty a firm might face. Product demand uncertainty may not be the primary. Maybe we want to think about cost uncertainty. Maybe we want to think about, we'll talk a little bit about strategic uncertainty, although I'm going to sweep most of that under the rug and tell you to go look in the appendix about that. But there are all kinds of uncertain forces that firms face. And so this is just an example of one that was simple to model. But the general principle is that information reduces this kind of uncertainty and many kinds of uncertainty that firms face. So the second ingredient is, I want this uncertainty to be relevant. So I'm going to have firms that price risk. And this is a pretty unusual assumption for this literature. But for any of you who have ever taught MBA students, or students who are going to go out into the business world, they all learn to price risk. They might not remember years later exactly how they were taught to do it, but I don't think anybody graduates from something like an MBA program without having absorbed the message that risk carries a price. So this isn't sort of a theoretical abstraction. This is something that managers are doing and systematically are taught to do. So firms then choose an upfront investment, and then they choose how much to produce. So this is going to be like a two-stage model. First, I'm going to choose how big a factory to build. And then I'm going to figure out, with that factory, how many blue shirts or how many black shirts or how many pink sweaters I want to make, given the data that comes in. I would like to make this more dynamic. I'm moving in that direction. We can talk afterwards about what that might entail and what kinds of things might change. But one has to first understand this kind of static problem before you can move to thinking about, what are all the dynamics of this. But it's an interesting direction to go. I'm not doing it today. So then data will have these competing effects on markups. The first is, growing big is really risky, right? You want to make a huge investment in an enormous firm that'll produce, lots of shirts at low marginal cost. That's great, but it's a big upfront cost. You know exactly what the revenues will be. So data is going to help firms to reduce this kind of risk. High data firms then are going to choose to be bigger, right? If it's less risky, because data helps you make good forecasts, then they're going to do more of this, big investment up front. And so when they choose to be big, that's going to push markups up. But at the same time, producing many units is also risky. So if I decide I'm going to, do a run of 1,000 blue shirts, but I'm pretty uncertain about what the demand for blue shirts is, that's a little scary as well. So data allows firms to predict demand well. It's going to encourage them to produce more units. And this we'll call the risk premium effect. It's going to lower, when they produce more, it will lower the equilibrium price of the good. So those are our two competing forces. Initial investments big is pushing markups up, but big runs and big production, scale is pushing equilibrium prices down. So we can't really look at markups and say, aha, that's got to be data, right? Because it could go up, could go down. Not right, not the best indicator. What we do want to look at is the composition effects. So firms use data to produce more profitable, i.e. higher markup goods. That's what they want the data for. They want to profit from it, right? That's their incentive. So if they use data to produce more profitable or more high markup goods, it means that data is creating a composition effect in the basket of goods the firm produces. That's why the firms want the data. They want it in order to create composition effects. And it's these composition effects that are going to change what's happening with measured markups at various levels of aggregation. Some level, we already knew this, that if we measured markups in one way, they go up, and another way they're flat. There's got to be something about composition going on. That's not a new insight, right? But this is a theory for exactly what the nature of those composition effects might be and why they might be growing over time. And similarly, pro-cyclical product and counter-cyclical firm or industry markups can arise if we think of recessions as being times when there's high variance. There's going to be more scope for composition effects, more scope for covariances in a really high variance environment. Okay, so those are the main ideas. Well, let's get into the model. There are NF firms indexed by I. So this is important only in that this is a finite number. So we're not talking about a perfectly competitive market. There's a product space that has N attributes, and each attribute is indexed by J. And then there are goods that are indexed by K that are some combination of attributes, right? So my shirt is a combination of a shirt attribute maybe and a blue attribute, or maybe a cotton attribute. And I'll have various weights of the shirt on each of those attributes. Maybe it's, 3 times shirt, half a weight on cotton, and 2 on blue. And so you could dispense with this, and we could just have each good as an attribute. It's just going to be awfully hard to take this model to the data, and I'll show you why. If you don't have goods being related to each other in some way. So think of attributes, goods, or if you want, portfolios of attributes, right? And attributes are like underlying arrow securities, right? And fundamental risks. So a firm is going to choose an investment, how big a factory to build, essentially, in lowering the marginal cost. So the bigger the factory you build, the more cheaply you can produce these blue shirts. The cost of building the factory is G. There's a parameter in there, chi c. The only thing that's doing in there is so that later on we can boost the marginal cost or lower the marginal cost by moving this parameter around. And ci, which is the marginal costs of the goods, or really of the attributes. So I can produce shirts more cheaply. I can produce blue more cheaply if I invest up front in a bigger, or let's say high-tech factory. And then they choose a quantity to produce, qi. So this is a vector of how many units of potentially every one of these K goods. It's not to say a firm has to produce every one of these goods indexed by K, but they can if they want to, and they're going to choose how many units of which goods to produce to maximize expected utility and utility. Why am I making a distinction between these two? Well, at the time they have to choose how big a factory to build, they're going to have different knowledge than at the time when they choose how many shirts to produce, let's say, or how many of all the goods to produce. They'll know what the value of all the data is at this point. So what is this utility? Well, the objective of a firm when it decides to how many units of each kind of good it wants to produce is expected profit, right? So they're expected profit maximizers. This is the cost, the initial setup cost of building the factory. So that's really part of expected net profit. And then we have this risk term in here. So minus rho I over 2, conditional variance of profits given the information set. So this is how uncertain am I about what the revenues will be from this factory, right? And the more information or the more data I have, I can condition on more in this information set. You want to think about a conditional variance as being like a forecast error, right? If you've got a bigger data set, you can make more precise estimates of your parameters, and you can make more precise forecasts. You'll have smaller expected forecast errors. A conditional variance is an expected squared forecast error. So more data is going to allow me to forecast my profits more precisely. It's going to reduce this conditional variance. And rho I is just a price of risk. Now, that could be that the firm prices risk because they've learned the CAPM. The manager says, I know that I should price risk according to the CAPM. It could be that the manager gets equity as an incentive pay, and they'd like to, they're personally a little risk averse and don't want to lose a lot of money. It could be that this firm prices idiosyncratic risk because it's worried about bankruptcy. Those are all possible explanations for why might a firm want to try to avoid an enormous amount of fluctuations in their revenue streams. Okay, so that's the firm side. There's a demand side. I'm not going to quite do justice by fleshing out all the micro foundations of this. I'm simply going to say there's going to be an equilibrium price, which is the customer's willingness to pay, that decreases, and this is really a marginal customer's willingness to pay, that decreases in the quantity that firms produce, right? Firms produce a lot. We've got to go way down the demand curve to be able to sell all of these units, right? So higher supply of apples, lower is the equilibrium price of apples. That's really all we're saying here. It takes a specific structure though. So this willingness to pay of the marginal consumer, which will turn out to be the equilibrium price, is some constant, right? There are different, this is the price by the way, for, for each of the attributes is a constant. So maybe, if blue is out of fashion today and everybody really wants purple, then the P lower bar for purple is going to be a lot higher than the P lower bar for blue. So this is just how much do we like this attribute. There's shocks to attributes. This is the uncertain piece. This is what firms don't know. This is what they're going to use data to try to forecast. And then this is a elasticity parameter times, this is how much all the other firms produced of the attribute blue or the attribute purple or the attribute shirt. So if there are tons of shirts out there flooding the market, there's a minus sign in front, we're going to have a low equilibrium price of, of shirts. Okay, so that's going to represent the demand side. So it's basically a Cournot model. The price is decreasing and the quantity other firms are producing. Everybody's choosing quantities, but it's in this attribute space and it's got some shocks to it to create the randomness that firms will want to forecast. So this is about the value of an attribute. The value of a good for a customer is just linear in the attributes. So if I said, I think I said this was, 3 weight of 3 on blue. So AJ for the attribute J of blue would be 3 for the shirt, which is Laura's blue cotton shirt, and so forth. So we'd have a weight, I think I said a half on cotton and 2 on blue. So we have these weights, and this is how much you value shirt, how much you value cotton, and how much you value blue. Right? And so the weights on each of these attributes will give you the value for a shirt that has these attributes. So then data is information about the demand shocks. It's about the BI. So it helps us forecast these BIs. So I'm going to exogenously give each firm a number of data points. Okay. So I'm sure you're wondering, well, wait a minute, where do the firms get the data points from? And why don't we write down a model about buying them or generating them, and all of that's really interesting. But my main question here is, what effect does data have on market competition? So if I want to ask something about the effect of data, then I want to hold data fixed. Well, no, fixed isn't the right word. Hold it exogenous, exogenously move it up and down and see how that changes my market outcomes. So data here is exogenous. Each firm I has ND data points. Each data point has noise that's independent across firms and independent across the BI shock. So each data point is a signal, really. It's a signal about that demand vector for all the attributes, that normal 0i vector, and it's got signal noise. Signal noise is mean 0, so that the signal is unbiased, and it's got a variance covariance matrix signal. So the information set then is all of the signals that I've ever seen. I am also here going to give firms access to all the signals every other firm has seen. This is really for simplicity. So what does this do? If I don't know all the data that other firms have seen, then I have 2 sources of uncertainty here. And what's the equilibrium price? I'm uncertain about the demand shocks, but I'm also uncertain about what my competitors will do. That's an interesting model with strategic uncertainty. We solved that model in the appendix. It doesn't change anything that I'm going to tell you qualitatively about how this model works. So then rather than solve a more complicated model where the mathematics are harder to see through and harder to connect to the results, we're going to solve a simpler model where I'm shutting down strategic uncertainty by letting you see everything your competitors know as well. But for some questions, that strategic uncertainty could be really interesting, and it absolutely is feasible to do in this setting. Okay, so that's the entire setup of the model. So solving it. First order condition in QI, how many units of each one of the various goods does a firm I want to produce? Well, this depends on risk, price impact, and expected profit. So let me start with the second term in this formula over here. The expected, how I want to produce more if I think this good has a high expected price relative to the marginal cost of producing it. The more profitable I expect it to be, the more I'd like to do it. Easy. But I'm going to divide that expected profit by 2 things. The first is the uncertainty. If I'm really uncertain, I still want to produce more of high expected price relative to cost goods, high profit high expected profit goods, but I'm going to scale back those ambitions a little bit because I'm a little scared about the risk that this entails. I don't know that I'm going to get this PI. I just expect to. So a lot of uncertainty will make me behave cautiously. And so we see we're dividing here, dividing by a larger number. That's my caution. The other thing that we add to this is my market power. How does my choice of quantity affect the equilibrium price? That's really my market power, right? If I produce one more unit, I'm going to push the price down. That's what a monopolist puts in their decision problem, and restricts supply, reduces Q to push up P. Okay, so this term here is getting at how competitive or uncompetitive is this market. Okay, so I'm going to define a term to be the sensitivity of production Q to a change in the expected price, this HI. This is just a simplified version. We put in the equilibrium value of market power here of this first term here. Okay, so HI is this first term, this inverse. And it tells you if price goes up a little bit relative to marginal cost, how much more do I produce? Okay, and H bar is simply the average H for each of these firms, because different firms with different amounts of data and potentially different DPDQs can have, could have different sensitivities. So notice here that then HI governs the covariance of expected prices and quantities. Okay, that's going to be an important feature that comes back in just a minute. So data shows up here in that conditional variance. More data allows you to estimate stuff better. It reduces your expected squared forecast errors. That's that conditional variance. So more data lowers this term. See, it's inverse, so it boosts HI. So more data increases the covariance between prices and quantities. That's an essential function of data here. It allows a firm to produce more of stuff that's going to be in high demand and really profitable to produce. That's why they like it. Okay. So then remember, the firm is making two choices here. This was how many units of each of the goods to produce. The other choice they make is how big a factory to build. So to think about that, we want to take the derivative of expected utility with respect to that marginal cost choice variable. Lower marginal cost here really means bigger factory. Okay, so two terms here. This is just the derivative of the cost function with respect to that marginal cost choice. That's pretty straightforward. This is the marginal cost of building a bigger factory that lowers your shirt production costs going forward. But the marginal benefit term is what's interesting here. So the marginal benefit of building this factory is bigger. Well, if you expect there to be higher profits from shirt production, you'd want to build a bigger shirt factory. That's not so surprising. That enters once, and that enters twice. But in the middle is that H term. Remember, data, lowered variance, inverse, pushes up H. Data makes this H term bigger. So a firm that has more data, that knows it's going to be able to forecast demand better, is going to be more inclined to build a bigger factory. Okay, so then this is what product markups look like. We can solve for them in this version of the model. They're rather simple. Let me start with the definition of a product markup. Okay, this is not a firm markup, but it's not an industry markup. This is for a particular product K produced by firm I. And the markup is defined as the expected price of that good, firm I's price, divided by firm I's marginal cost for that good. Okay, so we substitute in the equilibrium values of these, particularly the equilibrium value of the price, and we get this expression. Let me talk you through the expression by asking the question, what makes product markups large? So first is, if you've got lots of valuable attributes, right? If everybody's really big on purple shirts today and you produce the purple shirts, that's a high expected value of that P lower bar, that's going to get you a higher markup. The second is low price elasticity of demand. Not surprising, right? If we think that there's low price elasticity, that shows up here as a low H hat or H bar, we're going to get a markup that's higher. That's a very standard oligopoly logic. So nothing new in the logic there. But the third effect is the one that's new. So scarce data or a high price of risk. So scarce data, having a small number of data points, makes this variance large and makes H hat and H bar low. Or similarly, having the same amount of data, but having a higher price of risk, a firm that says, wow, I'm really averse to this uncertainty, will also make markups large. So one way of thinking about this is a firm in this model should not produce if they're just breaking even. Because if they're just breaking even or even have a small profit, that small profit is not enough to compensate them for the risk that they bear in production. So this is really looks kind of like a markup has a risk premium effect in it. A firm both might get markup revenue because of monopoly power, but even a perfectly competitive firm in this world can charge a positive markup simply to compensate itself for the risk that it's bearing. Okay, so what happens when we give a firm more data? So the first result is there's data investment complementarity. A firm that has more data chooses a lower marginal cost, meaning they're building a bigger factory. It's a higher cost investment, okay? And we saw that effect, oops, sorry, I had to go back. We saw that effect right here. More data raised H, raised the marginal benefit of investing in that large factory with the low marginal cost of shirt production. Okay. So then the second piece of this is that high investment in that big firm raises product markups. So more investment, meaning choosing a lower marginal cost in any attribute of a good, any attribute J of good K, such that good K loads positively on that attribute. Meaning if I invest in producing blue dye more more efficiently, or I invest in producing shirts more efficiently, or I invest in producing cotton more efficiently, any of those will increase the markup of the good that is the blue cotton shirt. Okay, so let's break this down. So this is just a representation of the result I told you. More signals of a given firm will increase that firm's markup on a product. But let's break that into the numerator, the expected price, and the denominator, the expected marginal cost. Both of these are going down, actually. So a firm with more signals, well, they invested in a bigger factory. So the whole point of investing in that big factory is to bring down their marginal cost. So that's not surprising that's going down. But now they're also producing more shirts and they're producing them more cheaply, and that's pushing down prices. So if prices are going down, why is the markup going up? Because the marginal costs are going down by more. So these big firms that are data enabled have really low marginal costs of production. Their prices aren't higher than other firms, but their prices are higher relative to their marginal costs. They're not passing on all of the marginal cost reduction to their customers. And you can see that here, right? If the marginal cost goes down a little bit, that doesn't go one for one into their choices. That gets modulated by the risk and the market power. Both of these things dampen the response that firms have to a change in the marginal cost. So that shows up as costs falling by more than prices fall, meaning the ratio of prices over marginal costs go up. Okay, but that's not the only channel. So that's pushing markups up. There's a channel pushing markups down. So if I hold fixed the size of the factory, I'm going to take that chi-c parameter that was in the cost function of the firm, where how big a factory to build, and I make that really high, or I make the risk price really high relative to that. I'm basically saying, don't adjust your factory size too much. Then an increase in any firm's data about any attribute of good K reduces the markup of good K. So if I hold fixed the factory size and I give this firm more signals, that alone pushes down the markup. Why is that happening? Well, this is supposed to be pretty flat. I kind of rigged it by pushing that cost of adjusting the factory really high. So I'm holding this piece fixed, and more data is pushing down the expected price, because you could think of it as the firm's now willing to go big on blue shirt production. If it has a pretty good sense, a pretty accurate assessment of what the demand for blue shirts is, it's going to produce more of them, and producing more quantity pushes the price down. Or you can think of it equivalently, right? These are both there in the mathematics, as this firm doesn't require as much of a risk premium. This firm sees blue shirt production as less risky. It's willing to undertake a big run of blue shirts for a lower price because it doesn't demand quite so much markup when it doesn't face quite so much risk. Okay, those are two ways of interpreting the same expressions. Okay, so there's one force that pushes markups up in data. Oops, there's one force that pushes markups down in data. What's the net effect? The net effect is that data increases product markups when risk prices are high, or when the marginal cost of investment is sufficiently low. Okay, so if you're really elastic in adjusting that factory size, or maybe this is the long run, right? And in the long run, we can adjust factory sizes a lot more. we should see data increasing product markups. But if we think that factories are hard to adjust, or maybe we're just thinking about a short run, and the immediate effect will be the risk premium effect, then data is decreasing the markup. So this depends on how elastic is this scale investment relative to the price of risk. So I don't know which way markups data pushes markups, where it pushes them up and down, but I know which parameters to look at that would govern this trade-off. We can ask a little bit about the market. What's the welfare effects of data? In the exercises I was just showing you, all firms were symmetric. And so in that world, data was unambiguously good, right? You can just see it. It's pushing down expected prices. I mean, sure, I guess here the markup is going up, but if consumers are facing lower prices, they're still better off, right? This just seemed all good. And that's fine, as long as the symmetry is preserved. That's really key here. So everything looks great with data in terms of consumer welfare, as long as firms are symmetric. If there's asymmetry in data, so if a firm that already has more data gets more of it, that's more nuanced. That can be good for welfare. It can also be bad for welfare. And that's a nuance that I don't have time to go into in a short talk, but is explored more in the paper. Okay, so I want to take the last third of the talk and talk about aggregation effects. So we've been talking about competing effects on product markups, right? What's the expected price divided by marginal cost for a particular product produced by a particular firm? Now I want to go to the next level of aggregation, which is the firm level markup. So a firm level markup is defined as the gross revenue of the firm, prices times quantities, divided by the total cost of the firm, quantities times the cost of each of the goods they produce. So we can break up this product in the numerator into an EQ, expected quantity, an expected price term, but we've got to, when we take the expectation of the product, we also need to keep track of the covariance. And here TR is the matrix trace, because this covariance is a covariance matrix. There are a whole bunch of products and a whole bunch of prices. So covariance here isn't just one number. We want the trace of that covariance matrix. Remember what I told you a few slides ago, that the whole point of data for a firm was to increase the covariance between prices and quantities. That's what they wanted data for. That's how they generated value from data, was to figure out which goods were going to be high priced goods and produce more of them. Well, that's exactly what this covariance is. So firms use data to create an aggregation effect, which makes the expected profit of price times quantities larger than the expected price times the expected quantities. It pushes up the firm markup relative to the markup of the goods that they're producing. So firms create aggregation effects. High data firms in particular create more aggregation effects. They push up their firm markups higher relative to the markups of the products that they produce. So data creates a wedge between product and firm markups for high enough chi-c, the parameter that governs the changing the size of the firm. An increase in firmized data about any attribute increases the firm markup relative to the average markup of all the products that that firm sells. Okay, so that's our first aggregation effect. Here's what it might look like. So as we get more data, this is like more data points for a firm. This is the product markup. It might be going down. It might not be. Remember, we said the data could decrease product markups. It could increase product markups. But what we always know is that it's pushing up the firm markup more than the product markup. So this could be both lines going down. This could be both lines going up, meaning more data is increasing product markups and firm markups. It could be one going up and one down, like in this example, but it's always creating more of a gap between the two. So data creates a wedge between the firm level and the product level markup. So the firm product markup gap is actually a really good measure of a firm's data. And one reason for that is every firm would like to achieve a high covariance between P and Q, right? That's what profitable firms do. They produce more of goods that are profitable, that have high prices. But that's not a measurable strategy. It's not a feasible strategy unless you have information about what the prices will be. So it is impossible It is not measurable. It's not statistically possible to have a systematic covariance between something you choose and some random variable that you don't know unless you've got some information about that variable that allows you to forecast it. Okay, so that's firm markups. The next level of aggregation is to go to industry markups. And here's where things get a little thorny because there are a bunch of different ways to measure an industry markup. You could say the markup in an industry is just the average of the markups of all the firms in the industry. That would be an unweighted average. So we'll call that M bar F. That's here are all the firm markups. I just described to you what firm markups were. We're going to add them all up and divide by N, the number of firms in the industry, unweighted average. You could say, well, I really want to count big firms more, right? And one way I might think about big firms is big firms are ones that have a lot of cost of inputs. So I might create a cost weighted markup where the weights are what are firm I's costs divided by the cost of the whole industry. So what are firm I's share of the industry as measured by their share of the total cost? And we use this as a weight, and then we weight each firm's markup by this share. Okay, so that's a frequently used measure. Unweighted markup, less frequently used, but it's out there. Cost weighted, frequently used. Sales weighted is another way to do this, right? You could say, well, sure, I'd like to weight big firms more, but I don't want to weight them by their share of the total cost. I want to weight them by their share of the total sales. So here's firm I's gross revenue divided by the gross revenue of the industry, and that's going to be their sales weight. And finally, there's a fourth measure of markups, an industry aggregates markup, where we just say, let's just take the whole gross revenue for the whole industry, add it up, and divide it by the whole gross costs of every firm in the industry and create the ratio of those two things. So kind of treat the industry as though it were one firm. Okay, and that's the industry aggregates markup. Okay, so growing data operates on all of these things. It increases the wedges between them, between the industry markup measures. So I'm going to hold the firm's investment fixed, or you could say for high enough, high C. I'm not going to let them scale up and down the factory too much. An increase in firm I's data about any attribute increases the difference between the cost weighted and the unweighted firm markup. It increases the difference between the sales weighted and the cost weighted markups. And it increases the gap between the sales weighted and the industry aggregates markup. So it creates all these wedges because it operates exactly on those weights. So firm to cost weighted, well, high data, high markup. Remember, I told you high data firms invested in being big and they produce more units of the goods that they did produce. They produce more, right? So they get weighted more and they have bigger markups because I told you that high data firms skew the composition of their goods towards high markup goods. So now we're weighting big firms with high data that systematically have high markups by more. The cost weighted to sales weighted. Well, high data, high markup firms have even more sales relative to their costs. So their sales weights are bigger than their cost weights because these firms operate really efficiently and have higher markups. So they have higher prices relative to costs. So it operates on that weight relative to the cost weight. And the cost weight in an industry aggregate, it turns out you can prove should be the same in theory. They don't come out exactly the same in the data. Nothing measured, similarly ever does. But that's why the sales weighted relative to the industry aggregates has a wedge because it has the same wedge relative to cost weighted. Okay, so this is what the model suggests, that we should see sales weighted markups go up by most, industry aggregates and the cost weighted go up in the middle, and the average firm markup go up by the least. And again, these could be, the model says these could all be going up, probably not all going down because you're getting significant aggregation effects. So I could probably pick some parameters, make that happen. It's not about how much they go up or down, but the fact that there are wedges between each of these, which is the strong prediction of the model. And this is what we see in the data. So this is from DeLocher, Eickhout, and Unger. We see the sales weighted markup going up strongly. The variable cost weighted markup, not so much. Sales weighted markup relative to the industry aggregates markup, again, a large and growing wedge. Most of the sort of, hyperbole, the concern about markups is about what's happened from 1980 relative to what's happening in the 2020s. And 2/3 of that increase is not from the industry aggregates measure, not from the variable cost weighted measure. It comes from the difference between the sales weighted measure and these other measures. It comes from aggregation effects, from weighting large firms that have high markups by more. And this gives you a way of thinking about why those weights might be rising. Okay, so last point, cyclical markups. There's another markup dispute besides the trending markups. There's a cyclical one. Bill says markups are counter-cyclical. He's measured them at a disaggregated level. Ramey and Nicarta say, sorry, that he's measuring them at a firm level or higher, firm level or industry level. Ramey and Nicarta say there's no evidence of counter-cyclical markups in the disaggregated data. This is a big deal because these counter-cyclical markups tend to be pretty important for the operating of new Keynesian models used by central banks around the world. Suppose recessions are times when demand falls, sure, but importantly, demand variance or uncertainty rises. If that's the case, then both of these can be right. Product markups could be flat or even pro-cyclical, and the firm or industry markups can still be counter-cyclical. Okay, so the proposition is simply that markups diverge when volatility rises. The product level markup converges to a constant, and the firm or industry markups asymptote to a function that is increasing in variance. So the more volatile the environment, the more those aggregated markups go up relative to the disaggregated ones. Okay, so there are two sets of facts measured in two different ways, and our model helps us think about why both of these facts might be true at the same time. So you can think of, on the x-axis here, recession to boom, boom being on the right, recession being on the left. What's happening here? Well, the product level markup could be going up, and the cost weighted markup could still be going down. Why is this happening? Well, over here, there's a lot of uncertainty. There's a lot of variance. Remember, the key difference between the disaggregated stuff and the aggregated stuff is a covariance. Covariances are bigger when there's more variance. It's kind of like there's more scope for assortative matching in an environment where there's a lot of heterogeneity in traits. Well, there's more scope for getting really high quantities when the prices are extraordinarily high and benefiting a lot from that if prices are pretty volatile. Okay, so there's more scope for getting it right and benefiting, going big, getting a lot, exploiting a lot your data, and producing a lot in times when prices are high, when you've got a lot of uncertainty, when you've got a lot of heterogeneity, when you've got a lot of volatility. That's what's going on here in recessions. And so the more aggregated markups reflect more of that composition effect that can be really big when outcomes are really different. Okay. I'm just going to mention that there's a version of this model where a firm can choose their location in the product space. So I presented a model to you where goods were fixed in their loadings on attributes. I said good K has, weight 3 on shirt and half on cotton and 2 on blue. And I took those weights as given. Firms could actually choose. Maybe I want a shirt that has weight 3 on shirt, but 2 on blue and only half on cotton. And I want to mix it with something else, right? And so they can choose the weights on each of the attributes, and that just gives it a different interpretation, as firms not just choosing how big a factory and how many units to produce, but choosing their location in a product space, right? And it makes connections with models that do that, and makes clear that these same results can arise in that sort of richer environment. And the reason is that firms are going to choose attributes with higher markups, just like they chose products with higher markups before. And product competition, raises the product markups for the same reason that it increased firm markups before. So really, this is just a rotation of the previous problem. Okay, so we started from a simple premise. Firms use data to predict what their customers want, maybe also predict other stuff that's uncertain about their environment, but firms prefer higher profits and they prefer lower risk. And that was a new ingredient in this model compared to most models of imperfect competition. And data does create returns to scale, exactly what people are worried about. And it prompts high markup firms to grow bigger and charge higher markups, and looks like more market power. But data also reduced risk, and it allocated production efficiently. It got firms to produce more of stuff that people really wanted. That's the good side of data, right? Data does help us get goods to people who value them. And the problem is this isn't really a separate force. You'd like to be able to just keep the good stuff and cut out the bad stuff. But the efficiency gains are what make the firms want to grow, which makes them big, which gives them the market power. So it's not so easy to just sort of chop it up and say we can sort of regulate the bad side and keep the good side. Maybe they're more nuanced approaches, but there's no obvious one. There are unexpected predictions from this. We did not set out to write a paper about markups at different levels of aggregation. That just sort of came out of thinking about, well, which aggregate markup do we want? And they give really different answers. And you know, I don't think anybody had connected the idea that data could help us understand, firms' use of data could help us understand why these various measures of markups behaved so differently. So firm and industry markups are more counter-cyclical and, you know, are trending higher. And all of this is supported by the empirical work that's already out there. So lastly, I just say data resolves uncertainty, right? That's its essence, it's information, it helps us predict stuff, right? That's what empiricists use data for, to get smaller standard errors and smaller forecast errors. And so, you know, part of this last bit is just a plea. I'd love for more people to join in the study of data economics, but don't ignore risk. Don't ignore risk, because that's sort of central to the essence of data. And it's pretty important to the functioning of firms. And reducing uncertainty or risk interacts with market competition in surprising ways. That's it. Any questions?